Problem 14 is a really common problem. It's asking you how fast this car needs to be going initially to when it reaches the top of the ramp, if it reaches the top of the ramp, to basically perfectly just stay on the track. It's not pushing up or falling down from that moment. It'll just continue to loop perfectly. So essentially, we have two state points. I'm going to call it initial and final. And we are really going to do a conservation of energy analysis here. And then we're going to have to use some other free body diagram work to synthesize that. But a few assumptions I'm going to make is everything here is frictionless. That's a good assumption to make unless they ask you to work in friction, which will make it a little more complicated but doable. And then I'm just going to write the centripetal acceleration equation right there. It's going to be important. The tool we'll use later. So starting off with just a kinematic equation. Not kinematic equation, excuse me, conservation of energy equation. Potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final plus work done. Again, that's where friction would go into this if you needed to use friction. No friction in this situation and no other work done in the system. We do have an initial speed. That's what we're looking for. We do have a potential energy. It's starting at some height. There will be a final potential energy because it's at some height upwards, and then there is speed. The car is moving in the final situation. So none of these are going to cancel it out. So we're going to start off with mgh plus 1/2 mv initial, or they call it v naught. I'm going to call it v initial, just to keep my nomenclature all the same. Mg times 2h is our second potential energy, plus 1/2 mv final squared. Both of these are squared, forgot that. Okay, so from this spot, we're looking for v initial, right? We can go ahead and solve for that in a second, but I just want to go through and look at all of the components. We know mass, we know acceleration of gravity, we have a constant for h. We know mass, we're solving for this. Mass, constant, constant, mass. This is the component we do not know. So we need to find this to plug in and solve. So if we're looking for v final, where can we find that? And this is where we're going to do a free body diagram. So if we take state point 2, where the car is at this point, right? It's moving directly to the left, and it is not coming off the ramp, and it is not pushing the ramp upwards, right? It's the point where it is perfectly just kissing the ramp as it goes around the circle. So that point right there is where the force downwards, which is just gravity, perfectly equals some upwards force. This is the centripetal force. It's not a real force, i.e. something being applied to the system. It's like a pseudo force, I think is the term for it, but you can still mathematically work it into your equation. So if we start from this point, we know that our centripetal force equals our gravitational force, right? And from here, we can find some work. We can find some velocity. So centripetal force is going to equal some mass times acceleration, centripetal acceleration, mind you, and our gravitational force is going to equal some mass times the gravitational constant, acceleration. So we know in this situation, our centripetal acceleration just equals our gravitational acceleration. And that makes sense because everything trying to increase our speed upwards is the same as our speed is increasing downwards, i.e. there is no increase in speed in the y direction. But we also know this is our equation for centripetal acceleration, and we can plug that in. So v squared over r equals g. And now if we're solving for v, because our v is going to be the speed tangential to your, that this v is the speed your object is going in the centripetal motion, right? And causing that pseudo acceleration outward in your circular motion, right? So v is just going to equal gr to the 1/2, right? And so our v, which is our v final, equals g times what is r? R is just one single h, right? The radius is just half of our circle, which is just h. And so now we know that the square root of g times h is our v final. So we can plug that into our original equation. So we have mgh plus 1/2 mv initial squared equals mg2h plus 1/2 m square root gh. squared. And I'm just going to go ahead and simplify this equation. Our m's are all going to get canceled. Canceled, 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 canceled. This whole situation is going to go away, and we're left with GH plus 1/2 VI squared equals 2GH plus 1/2 GH. There's a lot of GH's here. We can all simplify. So if we have 1/2 VI squared equals 3/2 GH, multiply by the 2, and you're going to get V initial equals the square root of 3 GH. So this is the speed you need to start in this situation to get this car to perfectly wrap around this ramp. Problem 15 gives us a block and a ramp problem, which means a free body diagram is incoming. But it asks us to consider kinetic friction. So the block is moving, but there is frictional force. And it's asking us to look for basically at what point the relationship between that coefficient of friction and the angle that the block is going to have no acceleration, a constant motion. So pretty simple. We're going to go through it real quick. I went ahead and drew our free body diagram already, mostly just to avoid doing art in front of you guys. But if this is our angle right here and our ramp, right, the black dotted line is our traditional horizontal x-coordinate. This blue line right here is going to be our new frame of reference y-coordinate system, and then this line right here is our x-coordinate system for our new frame of reference. We have two forces in this new frame of reference. We have normal force pointing always perpendicular to the ramp or the surface you're on, and then frictional force, which moves always points opposite of the direction of motion. So block's going to slide down the ramp, frictional force is going to point to the left. Right here I have the force due to gravity always directly down, but then I drew in the components of it to match our new xy coordinate system. One thing I just want to highlight when you do ramp problems like these, if you draw your free body diagram exaggerated, you always have like one small angle and then one super big angle. So like if this is our theta, it's very easy to see that this right here is theta. So you don't have to do that weird like holding your hands up and tipping it to figure out which component is going to have the theta, right? You know, is it this section or is it right here that has like the angle given's value? If that makes any sense. The more exaggerated you draw, you know, this small angle is always going to be theta. The big angle is going to be the opposite theta, right? Okay. Moving forward, we're going to just use we're going to do our two Newton's second law equations, right? And we're just basically draw out our forces. So F in the y direction equals mass times acceleration of the block. And remember, y is going to be these forces right here. So positive directions up is going to be the normal force minus mg cosine theta. And if we go ahead and do our x direction, it's going to be the sum of the forces in the x direction equals mass times acceleration. In that equals, let's see, positive. I'm going to call positive motion down the ramp. So positive motion is going to be mg, I'm not writing anything, mg sine theta minus the frictional force. Okay, so if we go ahead, we know that the block is not moving off the ramp. So this equals 0. And I can set Fn equal to mg cosine theta. I'm going to make these two different systems, different colors. All right, down here, we also know this system is going to equal 0 because we want a constant acceleration with motion, but a constant acceleration. So we now know the frictional force is equal to mg sine theta. We also know the formula for frictional force is the normal force times the coefficient of friction, in this case, kinetic coefficient of friction, mg sine theta. We're going to plug in this value for the normal force, so we get mg cosine theta times the coefficient of friction equals mg sine theta. And now we can go ahead and simplify this, and we get coefficient of friction equals the tangent of theta. So this is the relationship that keeps the block at a constant velocity. So there you go.